In this video, let us understand Radon-Nikodym theorem, a topic that sounds incredibly intimidating, but is one of the most elegant and powerful ideas in both mathematics and finance. Think of it as Rosetta Stone of measurement. It allows us to translate from one system of probability to another, which, as we'll see, is the magic trick that makes all of modern derivative pricing possible. Let's demystify it together. Before we get into the theorem, let's quickly define a measure. A measure is just a formal way of assigning size or weight to things. The length of a ruler, the area of a field, and most importantly for us, the probability of an event are all examples of measures. The Radon-Nikodym theorem tackles a very specific problem. If you have two different ways of measuring things on the same space, when can you express one in the terms of another? In other words, can you find a function that acts like an exchange rate to convert from one measurement system to another? Now, you can't just convert any two measurement systems. There is a critical condition that must be met first, and it's called the absolute continuity. Let's say we have two measures P and Q. We say that Q is absolutely continuous with respect to P if any set that has zero size under P has zero size under Q. The best way to think about this is the no miracles rule. Imagine P is a recipe's ingredient list and Q is the final weight of the cake. If your recipe calls for 0 grams of flour, you can't magically end up with a cake that has weight from flour. If P says an event is impossible, Q has to agree. You can't create something from nothing. So, if that no miracles rule holds, the theorem kicks in. It states that if Q is absolutely continuous with respect to P, then there exists a unique function, which we'll call f, that lets us convert between them. So QA can be shown as integral of f dp on the space A. This formula might look a bit scary, but the idea is simple. It says you can find the size of any set A under the measure Q by calculating the weighted average of the size under measure P. And what provides those weights? The function f, which we call the Radon-Nikodym derivative. Think of the currency exchange rate analogy. Let P be the US dollars and Q be euros. The Radon-Nikodym derivative, dq by dp, is just the EUR-USD exchange rate. It tells us how to reweight your dollars to find the value in the euros. Okay, so why does a quant or Wall Street care about this abstract math? Because it is the mathematical bedrock of modern derivative pricing. In finance, we use two different probability measures or worlds. The first one is the P measure, which is the real world. This is where we live. It describes the actual probabilities of stocks going up or down. And these probabilities includes a risk premium, the extra return in versus demand for taking on a risk. The next world is the Q measure, which is a risk-neutral world. This is a synthetic imaginary world we construct purely for pricing. In this world, we pretend everyone is risk-neutral, which means the expected return on every single asset is just the risk-free rate. This simplifies pricing enormously. And how do we legally jump from the real world to this magical pricing world? We use the Radon-Nikodym derivative. The Radon-Nikodym derivative is a tool that translates the P probabilities into Q probability. It effectively strips out the risk premium, allowing us to price any derivative by simply calculating its expected payoff and discounting it. Now, let us make this crystal clear with a simple coin toss example. In a notebook, we have a space with two outcomes, heads or tails. Where P measure, the real world, is a biased coin that lands on its head 60% of time. Our Q measure, the risk-neutral world, is a different system where the heads has a probability of 75%. First, we check for absolute continuity. Since no outcome has zero probability in P, the condition holds. Now let's calculate the Radon-Nikodym derivative, or the exchange rate for each outcome. The calculation is done in the code. The code simply divides the Q probability by the P probability for each outcome. We get the derivative of 1.25 for heads and 0.625 for tails. Finally, let's verify the theorem. It says that Q of heads should be equal to the derivative of heads multiplied by P of heads. And there it is. 1.25 times 0.6 gives us 0.75, which is exactly our original Q probability for heads. It works perfectly. We have successfully used the derivative to convert from one measure to the other. So the Radon-Nikodym theorem is far more than an academic exercise. It's the rigorous foundation that allows financial engineers to define and justify the existence of a risk-neutral world, translate between real-world probabilities and the artificial probabilities used for pricing, and build a consistent framework for arbitrage-free pricing. It truly is the Rosetta Stone of measures, allowing us to understand the language of one word through the dictionary of another.